Yeah, I looked at combination of assignments and people that had done the practice tests and found, looked like the kind of the handful of problems that seemed like they were causing most trouble. And not for everybody, but for a significant portion of people, it seemed like there were just a few issues with some of these. So I thought real quick before our test tomorrow, I would just run through and run through a few of these and just kind of zip through them quickly, and we can talk about them a little bit, but I more than anything just wanted to power through a few of these so you could get one last viewing of how to do these things. And then at time permitting at the end, I wanted to just kind of reach ahead just a little bit into the next section, just kind of get a brief introduction. We'll continue more with that on Wednesday. All right, so something like this, find the limit. Real quick, what do we always do when we're trying to evaluate a limit first? First thing we always try.
Substitution.
Direct substitution or direct evaluation. So we're gonna try that. Doesn't work here, right? We get 0 over 0, more work. So we got to do something. What's the something gonna be in this case? What do we do if we've got radicals in here like this? What's that kind of trigger? Say it again. Conjugate, good, right? We're gonna multiply top and bottom by the conjugate of the factor that's got the square root in it, right? So in this case, here, I'll just do this. How about if I just I'll make that, I'll make this a dot, so that's our product symbol. And we'll just multiply by 11 plus the square root of x divided by the same. Right? Okay, what's that going to give us on the top? If we multiply conjugates, we always just fold, right? The O and the I cancel. Good. First term squared, so 121 minus x over, on the bottom we've got x minus 121 times this other factor. Okay, and so what about that right there? What do we got? How am I going to deal with that? Those want to cancel, but they don't exactly cancel yet. What do I have to do first?
Factor out a -1.
Good. Factor out. Does everybody see that? Factor out a -1. And all that's doing algebraically, just quick reminder, if we're factoring out in algebra 1, all that's doing is just changing all the signs of each term, right? So we could make this on the top instead. We could just make this a negative, the quantity x minus 121, right? And now we get our cancellation. So now we get this and this. And so I end up on the top with just a -1. Right? Make sense? And so at this point, I wouldn't even have to really write this step, but I've got the limit of, on the top, -1, and on the bottom, 11 plus the square root of, x. And now what can I do?
Substitute.
Now I can take my limit. It's no longer indeterminate. Now I get an answer, right? Square root of 121 is 11, so on the bottom I get
22.
Yeah. There's my answer. Right? Okay? All right. Questions? Good? Okay, what do we do with these kind? What do we do with these kind? We got a bunch of fractions. Common denominator. Good. Yeah, we're just going to simplify normally and cancel like factors when we get the chance, right? So on the top, what am I going to do on the top? What am I going to do to this first fraction? What's my common denominator going to be?
6 times x plus 6.
Oh, okay, so I multiply this one by 6 over 6. Good, so I'm going to get, if I do that, I'm going to get 6 over 6 times the quantity x plus 6 minus, and then this guy multiplied by the quantity x plus 6 over x plus 6, right? Then on the bottom, I just have an x over 1, right? So when we're dealing with fractions now, I've got my common denominator. On the top, I've got my common denominator of 6 times the quantity x plus 6. I'm just doing that, right? So what's that simplify to? Say it again?
6 minus x plus 6.
6 minus the quantity x plus 6. And if I go ahead and simplify that, what's it turn out to be?
X.
Negative x.
Negative x. Okay, if I distribute that negative sign, the 6's will cancel. So I'm going to get a negative x over my common denominator, right? On the bottom, I get an x over 1. What do? Once I get it down to a single fraction, albeit ugly, on the top and a single fraction on the bottom, what do I always do?
Times by yourself.
Good. Flip and multiply the bottom. Right? So I end up then with a product instead of quotient, which is handy. And I've got my negative x over 6 times x plus 6 times 1 over x. I just multiply fractions straight across, so I can cross cancel, right? So I can do that. And I got it. My x is canceled. Now the indeterminacy is gone. I can evaluate directly. On the top, I get what? Negative 1. On the bottom, if x goes to 0, I get 36. 6 times 0 plus 6, so 6 times 6. We got it. Okay. Good. Questions? Okay. Okay, how about this? There's a couple of them on here, and yours might, yours may not look exactly like this. There's a couple different forms this question can take on the test, but they all essentially get at the same stuff. And what we're looking at here is just sort of the ant analogy, right? We're looking at limits as approaching points, and you gotta remember, what are our 3 places where limits are undefined? Limits don't exist when, what happens to the function? See if you remember that. 3, or you have to, you can even just think about it. The 3 places where limits, and just think about this, these would be the 3 places where ants approaching from different sides wouldn't anticipate stepping on the same spot. Okay, breaking the function, good. Vertical asymptotes, so some kind of unbounded behavior. Then there was one other kind of weird one. Oscillating behavior. Yeah, where it just oscillates infinitely. Okay. All right, so what about this thing? True or false? The limit of f of x, graphed in blue, as x approaches negative 3 plus, what's that plus sign mean? From the right, equals 9. So there's negative 3. Is that true? Yeah, it is. As an ant's walking along this function from the left, he anticipates stepping on a y value of 9, right? That's true. What about this? True or false here? The limit of the function as x approaches 0 from the left equals 4. Here's the ant walking along the function from the left. Where does he anticipate stepping as he approaches x equals 0 from the left?
0.
0. Good. Now where would he actually step?
4.
4. Does that matter? Not as far as the limit's concerned. Good. So this is one where the limit actually is not 4. It's 0. And so that would be false. Okay? Make sense? Questions on that? Because you got to remember, the limit is about where the ant thinks he's going to be, not at all where he actually is going to be. Okay? Next one. True or false, the limit of f of x as x approaches 0 from the left equals the limit of f of x as x approaches 0 from the right. That's true, isn't it? From both directions, the ants anticipate stepping on y equals 0, right? So that's true. So then, true or false, based on that answer, the limit of f of x as x approaches 0 exists. True. True. Even though that's not where the ant is going to be, the ant anticipates stepping on the same spot from both sides, and therefore the limit from both sides is 0. It exists. the answer in agreement, right? True or false, the limit of f of x as x approaches 0 is 0? Well, it's true, isn't it? That's what we just said. Those all essentially are answering the same question. Yeah, that's where the ant thinks he's going from both sides, so yeah, that's it. True or false, the limit of f of x as x approaches 3 is 9. You gotta be careful with this one. The limit as x approaches 3 is 9. Is that true or false? It's false, isn't it? Right? Why is that false? Say it again. It's only true from one side. Good. Now, what if we had said, another one, what if we had said true or false, the limit as x approaches 3 from the, or excuse me, approaches negative 3 is 9?
False.
That would also be false, wouldn't it? Because the ant can't even approach from the left. The only way that one works is if I define it as a one-sided limit. Right? Okay, good. How about this, last one? The limit of f of x as x approaches 6 from the left is 6. X approaches 6 from the left, is the limit 6?
No.
What is it?
0.
0. Right, the y values we're looking for is 0. Make sense? Okay, good. Okay, this one. This one, people had trouble with this, I think, because they were trying to maybe make this one more difficult than it is. What happens with this here? Now, if I shouldn't say it that way. It doesn't fit the special limit pattern that we talked about. It relies just on cancellation of factors. If I try to evaluate this directly, what do I get? What's the tangent of pi fourths? If we look at quick unit circle, and you can always, this is always a good idea maybe, just to make a quick sketch. So if we're right here on the unit circle, what are the x and y coordinates at that point?
Square root of 2 over 2, square root of 2 over 2.
Good. Square root of 2 over 2, square root of 2 over 2. So tangent is just the y coordinate divided by the x coordinate. Well, they're the same. So what's the tangent?
1.
1. So I get 1 minus 1 is 0 on the top. Sine x minus cosine x, they're the same. So that's 0 on the bottom. So it is indeterminate, isn't it? Okay, but this is not one. Remember that the ones that we did in class always relied on our special limits, which look like this. The limit of sine theta over theta as theta approaches 0 is 1. Good. And the other one, limit of 1 minus cosine theta over theta as x approaches 0 is what?
0.
0. Good. So those are the two kind of special limits that we can rely on. But neither of those is going to work here because x is not approaching, x or theta or whatever our argument is, that in this case is x, is not approaching 0. So what do we do instead? Suggestions. And here's kind of the red flag you're seeing. You're always looking for, what's the, what about that?
Sine and cosine.
Yeah, good. We'll write that in terms of sines and cosines. Okay. We're going to do some, as we move on and get into some more trig stuff later in the year, I will do some fairly significant review of trig, and I kind of want to give you my little shot at the unit circle. I'm a big fan of the unit circle. You can do all of the trig that you essentially learned last year can be summarized on the unit circle, and it's really cool how you can do that. So we'll take a day at some point and just do nothing but trig and look at really how we can use that unit circle to great advantage. And then I want to talk about solving trig equations a little bit as we go along too, because there's more of a need for it. We don't really need that yet, but we will. So if we rewrite this in terms of sines and cosines, always a good idea. What do we get? Well, on the top I get 1 minus sine x over cosine x over sine x minus cosine x. And so really, if you think about this now, once we rewrite that composite trig function in terms of sines and cosines, this starts to look an awful lot like a problem. It's got some trig functions in it, but it looks in form at least an awful lot like another problem we did right there. Right? It's got fractions. What was our strategy with fractions?
Common denominator.
Yeah, simplify the top, simplify the bottom, flip and multiply, right? It's gonna work here too, so that's the idea. So what could we do on top then? What's our common denominator gonna be? Cosine, right? So 1 is just gonna be cosine over cosine.
Yeah.
And so doesn't this whole numerator then just become cosine x minus sine x over the common denominator, cosine x, right? All divided by sine x minus cosine x over 1, right? Okay, if I flip and multiply, make sense?
Yeah.
If I flip and multiply, do you see it coming?
Yeah. I got you. Easy.
Okay, so look, we almost get the cancellation. What do I have to do to make it happen though?
Got negative.
Yeah, once again, I just factor out that -1. So this becomes negative the quantity sine x minus cosine x, right? And now I get it. Okay, now I've got cross cancellation there, like I need. So that goes away, that goes away. I end up with a -1 on the top again.
Yeah.
Right? And now I can evaluate the limit. Now I end up with limit of -1 on the top, cosine x on the bottom, as x approaches pi-4. What did we say the cosine of pi-4 was?
2.
Square root of 2 over 2. So -1 over root 2 over 2. Flip and multiply. And what's that simplified to? What's 2 divided by the square root of 2? 2 is really just the square root of 2 squared, right? So can I just cancel, right? So just negative
Yes.
square root of 2?
Yeah, I
Make
got
sense?
you. Yeah, I got
Okay.
you. I got you.
We got it. Yeah, that's definitely a step above the other ones because it also involves anytime you're involved in trig stuff, it just adds that extra level that makes it a little tougher. But I promise you that it won't be long before you don't even break a stride doing trig stuff. I mean, it's once you kind of get a handle on feeling a little more comfortable with the unit circle and those trig identities, which we will. I'm going to force you to. We'll do is, like I say, a little trig review, and I'll probably even give you a little trig test to just kind of force you to memorize a few things. But your comfort level goes up dramatically with more practice. Okay, questions on that? That makes sense? Okay, and this YouTube video will be up today, so you can look at it tonight if you want to. Okay, now, moving on, that was the non-graphing calculator part. Now we're moving on to the graphing calculator part. And this is one where you can legally cheat with the graphing calculator. I mean, it's okay, I want you to, really. This is one where I want you to use all the tools available on the graphing calculator just to get answers. These tests should always be much easier, I think, than the non-graphing calculator tests as you get more comfortable with these graphing calculators, because so much of it can be, the analysis can be done on there. So what do we do? What are some things we could do? Let me pull up my graphing calculator, and let's just talk about this. What are some ways that I can, and I'm looking for the easiest way to do this. What are some ways that I can utilize the capabilities of the calculator to just get an answer quickly and easily? While it's popping up, just think about that. Now, let's first maybe briefly just think about the math. So where are vertical, it's supposed to say vertical asymptotes, I cut that part off. But where would vertical asymptotes exist? And this is the part you do have to be familiar with, the analysis you gotta cover. If I've got a rational function, where am I gonna get vertical asymptotes? Where we have what? Okay, zeros of the denominator, but there's an important thing I have to remember about the numerator then. Zeros of the denominator, but not the numerator, right? Shared zeros, top and bottom, are not gonna be vertical asymptotes. What are they gonna be? Poles, yeah, different, right? So if I get shared zeros, those are not what I'm looking for. I'm looking for unique zeros of the denominator, right? So what are what's probably the easiest way to go about finding them on a graphing calculator? Go to y equals, okay, so I could just graph the whole thing, but why even mess with that? Because it might be hard to spot exactly where the vertical asymptotes are. Why not just graph maybe the top function and the bottom function separately and just find the zeros graphically, okay? Or, here's the other thing, and maybe that's one thing we should just do today too at the end, is just make sure everybody's got this program. Let's look at it graphically first. I'm gonna go a little bit overkill with this because I really want you to be feeling comfortable with these graphing calculators. So if we graph the numerator, x squared plus 3x plus 2. Well, I guess also, do we even need to graph that one? Where are the zeros at the top? In this case. -2 and I want to find, because this factors, doesn't it? What two numbers multiply if I take the top? What's the top factor into? Good, so x plus 2, x plus 1, so my zeros would be -2 and -1. Now I could, if I wanted to, I could easily also just see that if I go zoom 6, there it is, right? Just so, what if this were an example where they weren't nice integers though? Maybe it didn't factor. Just to kind of explore how we could use the calculator to find those easily. Do you know how to do that graphically? Maybe not? Okay, I'll show you. We just want to find the x-intercepts, right? The zeros. For one thing, that's a little bit hard to see right there where those exactly are. And so I want to make my window bigger. Let me show you a great trick. If I go to the zoom menu, there we go. The first option, zoom box. Do you know about that one?
Yeah.
Okay, zoom box is great. Just in case you don't. If I hit zoom box, I can generate a window sized to my personal specifications. So there, I'm going to make that the upper right corner of the window. If I hit enter, and I'll just drag out a box that's going to be the window, my new window. Okay, that's probably good right there. If I hit enter, it'll graph it. Now I can see the zeros much more clearly, right? So all I've got to do is just go second, calc, to get to the calculate menu. Which option do I want? 2, good, which is 0. And then I'll just, if I want to find the left boundary, let's go ahead and find this one because I already have a left boundary defined. Remember that the left boundary just has to be an x value to the left of the 0, right? So that's a good example of a left boundary. I can also just type in an x value if I want to, if I know one that'll work. In this case, maybe I can't see on the graph where one's going to be, but if I knew one, like let's say I knew that 0.5 was going to be, I could just go 0.5 and just hit enter. Did you know that? It'll accept that.
What?
Oh, maybe it won't. What did it do? Oh, whoops. That's what I wanted to write. -0.5. There we go. And so look, it even sets up now. I can see that the 2 points. I've just captured everything in between. My guess, just any place in between on these simple functions is fine. There it is. Okay, make sense? Okay, so I could do that, top and bottom. Here I probably don't need to. That bottom factors also, doesn't it? What's the bottom factor into? Two numbers that multiply to -20 and add to -7. Oh, does it?
No.
Oh, does doesn't. Okay? That doesn't factor. Okay, so let's look at, so we need to rewrite the top one then. We'll write it as x squared minus 7x. Minus 20. Okay, and let's go zoom 6. Okay, and so these are pretty clearly going to be my. I know it's not going to share any zeros. Well, actually, I don't know that. It might share one. Yeah, negative 2. It's going to share, isn't it? Yeah. So if I found these, it looks like there's only going to be 1 0 of the bottom. Is that really on negative 2 though? Let's see. So we'll go like negative 3 for my left boundary, and negative 1 for my right boundary, and negative 2 for my gas. That's a lot quicker to do, isn't it? Having to trace. So no, it actually doesn't. Okay, these are both going to be 2 unique zeros at the bottom. Whatever. So negative 2.17. It's going to want these as. Remember what it said on this?
2 decimal places.
3 decimal places. 2. Okay, so we would just round these. Negative 2.18. Go find this one. Right? Make sense? Okay, there's another program for that. You guys have Aqueduct, right?
Oh, yeah.
You guys all have Aqueduct?
Yeah.
Okay, here's another one, really good one. If you go to Polysmolk 2, if you don't have this one, maybe I'll shut things. As soon as I'm done here, rather than do anything new, I'll just give that to anybody that wants it. So if I go alpha P, I can skip down to the P's. This is really a good one. Press any key. See, it does a bunch of stuff, but the one we want is the polynomial root finder. So the order is just, what's the order mean for a polynomial? Highest power of x, good. So we can make this 2. Now this is what's kind of nice about this. Look, you can choose real, or you can choose imaginary too. That's kind of cool. And so in our case, we only want real on this one, don't we?
Yeah.
Right. We'll take fractions. Actually, we want decimals, don't we, for our zeros? Because it wants it rounded. So we'll choose decimals. We can even set it up so, how many places do we want it rounded to? Well, we said 2. Oops. Okay, so that's it. Then these soft buttons down here just correspond to the F keys, so I would just hit F5. Plug in the coefficients. So let's say we're doing the bottom. That's just going to be 1. See, look, A2 is the coefficient of x squared, A1 is the coefficient of x to the 1, etc. So 1, negative 7, negative 20. And then I just go solve, and I get it. Isn't that cool? That's a good one. Okay. So I'll put that on. You can check real quick. If you don't have it, we'll quickly circulate that one to everybody.
Yay.
Okay, last one people had trouble on at all. What do I do with this? This is just one of those. This one, your graphing calculator, doesn't help you a ton, although it does. You could graph this thing and you could just see, you could see what the ant's walking on, just by looking at the graph, right? You could kind of get a visual picture of the function. It is going to have a vertical asymptote, but you could see is he walking up or down, and that would tell you the answer. But real quick, how do we do this one analytically? If x is approaching negative 7 from the right, that's a decimal like what? Negative, is it? If I'm approaching negative 7 from the right?
Oh, 6.3.
Ah, exactly. Now you gotta be careful with those negatives, because I approach from the right, I've actually got an absolute value that's less than 7.
Okay.
That's probably where people make a mistake on this one. So on the bottom, on the top, I'm just gonna get some positive big number. And now I'm just gonna put a plus sign. I don't even care what the number is, just some positive big number. On the bottom, I'm gonna get Negative 6.99999 plus 7 is what? 0.
A little
Positive.
zero.
If it's like, it's negative 6.99999 plus 7, it's gonna be 0 plus or minus?
Plus.
Plus. It's still slightly positive, so I know it's blowing up. Positive over positive is positive, right? So it's positive infinity. Okay, make sense?
Oh, okay.
Okay, check your calculators real quick.
How do I